All right, so what do we have here? Well, so the square root of 4 or 3, square root of 4, square root of 5, square root of 6, etc. So in this case, we have a bunch of terms, so that we need to determine our general rule in this case. Well, so in this case, the general rule, we need to find out the expression that gives out these terms actually. Of course, well, we need to start with the correct notation. It has to be some curly braces to begin with. And well, so is there anything that stands out that you believe it should be in the expression? Well, they're all positive. So what else besides the positive? There's some square root, right? There's some square root. And let's start the sequence at n equals to 1 and all the way to n equals infinity. So that's usually how we start sequences, unless we have some limitations about the domain, etc. So in this case, well, so for n equals to 1, if I plug in 1 plus what number equals to 3 in that case? 2. That is n plus 2 equals to, well, n plus 2, the square root of n plus 2. Let's see if it works for the next numbers. Okay, what about n equals to 2? Is 2 plus 2 equals to 4? What about for n equals to 3? Is 3 plus 2 equals to 5? So it works, right? It works, yes.
Can we just start at 3 and then have it be on square root of n?
That's what I was going to mention, and that's what I mentioned next. So when it comes to infinite sequences, there's not only one way to express them. Like he mentioned, we can start our sequence at n equals to 3 all the way to infinity and have the square root of n. That's another way to express it. It's the same thing. And well, essentially what we're doing here is shifting the indices, and that's something we may need to do in an application depending when we want to combine sequences together. We may need to do this so we can have essentially like terms, that is having sequences having all of them they're the same starting index, otherwise we wouldn't be able to combine with them. All right, let's have a look at the next example. All right, so what do we have? 3/5, negative 4 over 25, 5 over 125, negative 6 over 25, 7 over 3125. So here we need to determine whether we can identify any pattern of numbers. I mean, like a sequence of numbers, a sequence of perfect squares, a sequence of powers of 3, powers of 2. Do you see anything here that looks like a pattern at all? Anyone? Powers of 5. We have powers of 5 in the denominator, right? So let's write those down. So 5, this is essentially 5 to the 0. 5 to the first. 5 squared, all right? Yes, that's 5 to the third, 5 to the 5, 5 to the 6. All right, what do we have in the numerator? So we have the numbers 3, 4, 5, 6, 7. So all these numbers in the numerator differ by 1. All right, what else do we have besides that? So we have powers of 5, we have the sequence of integers starting at n equals to 3. What else do we have? We have an alternating factor, right? Because there's a plus, minus, etc. So let's see if we can write a sequence term. So for sure, I'm going to leave a space for the alternating factor here. Of course, we have a 5 to the n, and that's going to start at n equals to 1 and going to go all the way to infinity. All right, so we need to find a rule for the numerator in a way that, well, if we plug in n equals to 1 to get the 5 to the first power for the first term in the denominator, well, somehow we have to get a 3. How do we get a 3 in this case? Plus 2? So n plus 2, and well, let's look for the alternating factor now. So we need to make sure that the first term is positive. Let's see if negative 1 to the n works for that. So negative to the first power, negative 1 to the first power, that's going to be negative, and well, we want our first term to be positive, so no, that's not going to work. However, if we fix this by adding a 1, n plus 1, that should do it. All right. So those are a couple of examples on how to get the general term of a sequence, and in this case, it's important to consider every single possibility of a pattern, you know, a sequence of even numbers, a sequence of odd numbers. Like in this case, we use the powers of 5, powers of 2, powers of 3, etc. Perfect squares, perfect cubes. So, before going to the next topic, which is finding the limit of a sequence, well, we need to understand how to work with factorials. You may have worked with factorials before, or maybe not. If you have taken a probability and statistics course, you may have worked with these factorials. Well, so what's the factorial? So we're going to have these numbers with an exclamation sign next to it. No, these are not excited numbers. So what do we mean by factorials in this case? So whenever you see n factorial, and I have a couple of examples here, what we do is multiply all the integers below n. For example, 5 factorial, we're going to multiply all the numbers 5, 4, 3, 2, 1, and whatever that result is, that's a factorial of the number. So notice how the factorials of these numbers get big pretty quick, actually. You know, just from the factorial, from 4 factorial, which is 24, to 5 factorial, makes a big jump in the size of the number, and even from 5 to 6 is 720. Really, really big numbers here. All right. So, but still, so we need to understand how to factor or how to work with these factorials, because there's more than one way to write the factorial of a number, especially when it comes to simplifying these factorials. Okay. So, for example, I'm going to take the number 6 factorial as an example. 6 factorial, well, number 1, you have 6 times 5, times 4, times 3, times 2, times 1. However, do you agree that all this bunch of factors from 5 to 1, it's the same as saying 5 factorial? So another way to express the number 6 factorial is 6 times 5 factorial. I'm going to write it again. Another way to write our 6 factorial is as follows. So I'm going to group these 3. Well, when I group these 3 times 2 times 1, that's the same as saying 3 factorial. So another way to write the number 6 factorial is 6 times 5 times 4 times 3 factorial. Well, which one is the correct way to write it? Well, it's not that one is the correct way, one is incorrect. That's going to depend on how do we want to use them to simplify a couple, or whether a numerator denominator of factorials. All right, so to see this in action, how about we'll look at some examples. So let's simplify 9 factorial over 7 factorial. So without the use of a calculator, this is what we're going to do. So instead of writing, 9 times 8 times 7 times 10, multiplying all these numbers to get a really big number, and then divide by 7 factorial, which is also a big number, 7 times 6 times 5 times 4, etc. Well, that's not the most practical way to reduce factorials. In fact, as a key, expand the largest of the factorials. That's the key here. All right. So what are we going to do here? So they're asking us to simplify 9 factorial over 7 factorial. Which of the two factorials is the largest? 9. So this is what we're going to do. We're going to do 9 times 8 times 7. Well, instead of going times 6 times 5 times blah blah blah, we're going to stop at the number that matches in the denominator. And notice how these 2 factorials, 7 factorial cancels out the 7 factorial, and we're essentially left with 9 times 8, which is 72. So without even the need of expanding the whole number, get a big number, divide by a big number, well, which we can do if we have a calculator with us, you know? But what if on an exam or something, on a quiz, you don't have access to a calculator to an exam? It's important to know how to simplify this by hand without even the need of expansion. And in fact, even if you had a calculator, it takes forever to reach that factorial function. Let me show you where is that on the calculator. So I would have to go, okay, let me clear all this. I would have to go 9 on math. I would have to go all the way to the probability functions and select the 4. And then I'm going to divide by 7 math and the factorial symbol, and of course that's going to give us the same answer, right? So all we have to do is expand over the largest factorial until we get a match here, cancel out those factorials that match, and just multiply all the numbers that we're left with. In this case, we were left with 9 times 8, which is 72. All right, let's have a look at another example, letter B, 12 factorial over 3 factorial times 10 factorial. So in this case, we need to decide what's the best way to simplify this. Of course, I mean, you can divide. You could do the 12 factorial and go all the way. I mean, this is one way. You don't have to write this one, by the way. 11, 10, 9, 8, 7, 6, 5, 4, 3 factorial over 3 factorial times 10 factorial. Well, we can cancel out the 3 factorial. However, do you see all this bunch of numbers that we're left with? It's still going to be a really big number over 10 factorial. Well, that's not, again, the most practical way to simplify. So I would go about the largest in the numerator, the largest in the denominator. So what's the largest in the numerator? Is 12 factorial or 10 factorial? I mean, what's the largest of the ones that I highlighted? The 12 factorial or the 10 factorial? The 12 factorial. So let's expand that one. So that's a 12 times 11 times 10, but because we have already our 10 matching with the factorial below, make that a factorial. All right? And well, that's 3 factorial in the denominator. The extra factorial, just leave it as 3 factorial. All right? So number 1, we may go about canceling these 10 factorials, and well, we will be left with the following. So I know you might want to multiply 12 times 11. That's going to give us a big number. But instead, how about we do the 3 factorial by hand? That's easy to do. 3 times 2 times 1. That's going to give us a 6. So that's a 12 times 11 divided by 6. And 12 over 6, that's a 2 and 1. 2 times 11, that's 22. And notice in this case, we didn't have to use a calculator at all. We didn't have to expand the whole factorial number, multiply every single number. All we need to do is identify the largest of the factorials and expand that one and cancel with one of the factorials. Preferably, cancel it with the largest of them so you can get rid of a bunch of factors in this case. All right. What about letter C? In this case, well, we don't have numbers, we have variables this time. So in this case, we still have to expand about the largest of the factorial. So we need to decide between n plus 1 and n. Which of the two factorials is the largest of them? The numerator or the denominator? The numerator. So we need to expand n plus 1, that's going to be n plus 1, times n plus 1 minus 1, which is n, then it would be n minus 1, and then n minus 2, n minus 3, n minus 4, etc. We would be subtracting one integer to every factor that we have. But wait a minute, I don't need to do all this many factorials, because check this out. When we expand the first, we end up with n factorial, which matches with the n factorial in the denominator, and we can simply cancel these n factorials, and n plus 1 is going to be our final answer. Let me give you another example involving variables. So, all right, I have something that looks like n plus 1, another n plus 1 factorial, or no, you know what, let's do n plus 2. N plus 2 factorial times or divided by n minus 2 factorial. All right? Okay, so we need to, number one, identify the largest of the factorials. Which one is it? The numerator. So n plus 2. So we will have to expand that n plus 2 and get the new factor by subtracting one integer every time we expand one factor until we get a match with the denominator. So this will be, so we start with n plus 2. Subtract 1, that's n plus 1. Subtract 1, that's n. Subtract 1, that's n minus 1. We're almost there, that's n minus 2. But because this n minus 2 already matches with the n minus 2 in the denominator, we can put the factorial symbol here. And we can go about the cancellation. N minus 2 factorial with n minus 2 factorial. And we're going to be left with n plus 2, n plus 1, n, and n minus 1. That's our final answer. So the idea is to simplify these factorial expressions so that there are no factorials in the end. We're going to use this in the next topic, which is finding the limit of a sequence. So we may get these sequences involving factorials, and later in further sections we will work with series that also involve these factorials. All right. The limit of a sequence, well, so the limit of a sequence is exactly the same as finding the limit of a function, except that the function behind the sequence is a function with a special domain, and that special domain is the set of all natural numbers, that is the positive integers. And well, so in this case, we just need to add a couple of pieces of information. So this is something we didn't do back in Calculus 1 when we found limits, you know. So when you found a limit, either the limit exists or the limit did not exist. However, when it comes to sequences, we need to add extra words that we're going to use later in the further sections as well with the series. So if the sequence has a limit, well, then the sequence converges. But otherwise, if for some reason that limit it's either infinity or does not exist, well, that sequence diverges. All right. So let's have a look at some examples. So we have a few sequences here, and then they're asking us to determine whether they converge or diverge. So limit of 4 minus 1 over 5 to the n as n approaches infinity. So we need to compute this limit. Well, so number one, so to evaluate this limit, we need to determine where is this term going to. Where is it going to? This one, 0, right? So now that we computed the limit, we no longer write the limit symbol, just those numbers we were left with. 4 minus 0, which is 4. All right. Letter B. Limit of the square root of n as n approaches infinity. Well, so essentially the square root of infinity, where is that going to go to? Infinity, all right? Infinity or does not exist, all right? So in this case, infinity. And well, when it comes to vocabulary here we say it converges and converges to that value, but otherwise diverges. So diverges to infinity. So there's no limit, in other words, all right? Blows up to infinity. Let's look at letter C. Let's see what happens with letter C. So what do we have? -1 to the n. And n starting at 1 and going all the way to infinity. So let's write this as a limit problem. Limit -1 to the n as n approaches infinity. All right, any ideas on where is this limit going to go to? Zero. Okay, let's write down one of the options. So 0 is one of the options. Any other ideas? Does not exist. It's going to be alternating, right? Because essentially this is what's going on. So if we observe the graph, for example, so for n equals 0, no, for n equals to 1, that's going to give us a -1. For n equals to 2, it's positive, and then n equals to 3, negative, positive, negative. So it's just bouncing back and forth between -1 and 1. So for this reason, the limit, well, it's not infinity, but it's dne does not exist. And recall, it's one of the options. It's either infinity or does not exist. And in this case, also diverges. All right. Let's have a look at the next example, letter D. What do we have? Polynomial over polynomial, that's 3n squared plus n minus 1 divided by 6n squared plus n plus 1. And in this case, n going from 1 all the way to infinity. And let's see, how do we go about this sequence here? Okay, so we need to write this down as a limit problem. 3n squared plus n minus 1 over 6n squared plus n plus 1, n goes to infinity. Any ideas on how to go about this limit? This is a Calc 1 limit, by the way. Is something. So that, well, actually there's a couple of ways to go about this one.
Because the 3 over 6.
So yes, we can use those. I mean, it's not necessarily shortcuts, but if you want to call them shortcuts, I mean, and that's also very heavily linked to what something you did back in pre-calculus when finding the horizontal asymptotes of a rational function, you know. So what you did, number one, is look at the degrees of the numerator and denominator. In the case in which the degree in the denominator is larger than that in the numerator, no matter what you do, that horizontal asymptote is 0, which is the same as saying limit as n approaches infinity is going to be 0. But when the degrees match, all you have to do is go with the ratio of the leading coefficients, and that's going to be our limit, 3 over 6, which reduces to 1/2. So in this case, the sequence converges. It converges to 1/2. Now the long way to go about this limit, one way is to divide out by the highest degree in the denominator. So what you did is limit n approaches infinity. That's 3. The largest degree in the denominator is n squared minus 1 over n squared, 6n squared over n squared, plus n over n squared, plus 1 over n squared. And then, well, you reduce those two, and well, you can start actually computing the limits. N over n plus n over n squared. The n in the denominator is larger, that goes to 0, 0, 0, 0. And all that survives the limit computation is a 3 over 6, which is the same as going with the ratio of the leading coefficient. So there were different approaches. So that's what we did when we computed the limits at n equals infinity back at the beginning of the semester in Calc 1. And I think in some cases you were forced to actually do this. In this case, in Calc 2 you can do it either way. If you identify right away that the degrees of the polynomials, numerator and denominator, they're the same, just go with the ratio of the leading coefficients. However, if the degree is 1 less in the numerator, well, that means the denominator is a larger value, has a larger degree, so that's gonna grow faster and it's gonna go to 0. But otherwise, the third case, whenever the degree in the numerator is 1 or more than in the denominator, that means the numerator is larger than the denominator, and that's just going to blow up to infinity. All right? So a couple of different ways to solve the same problem. Either way. Well, but of course, I would go with the first approach just for the sake of time. All right, let's have a look at the next example. So what do we have? 2 to the n over 5 to the n. Well, so let's write this as a limit problem. 2 to the n over 5 to the n as n approaches infinity. All right. So there's a couple of ways to go about this problem. Number 1, by estimation, and number 2, by looking at the graph, because, well, number 1, if we try direct substitution on this limit, we would get, okay, 2 to the infinity over 5 to the infinity, we would get the infinity over infinity indeterminate form, all right? So that means that we can go about the L'Hopital's rule in this case and try to simplify the expression. However, check this out. And you don't need to write this if you don't want. This is fine. So, okay, let me keep the same color. If we take the derivative in the numerator, that's limit n approaches infinity. The derivative of 2 to the n is itself 2 to the n times ln of 2. That's the logarithm of the base of the exponential function, and that's ln of 5 times 5 to the n. However, using the L'Hopital's rule in this limit is not going to simplify our work. In fact, it's going to making our expression even more elaborate than it already is. So if we do L'Hopital's rule again, all you're going to get is limit n approaches infinity, ln of 2 squared, 5 to the n over ln of 5 squared also. And then if you do it a third time, you will be just increasing that power of ln of 2 and ln of 5. So we won't be able to simplify this using the L'Hopital's rule. So, let me get rid of all this garbage here, because we're not going to use it. So there has to be another way to simplify this. Number 1, well, by estimation, which infinity is clearly larger than the other infinity? Is the infinity in the numerator larger than the infinity in the denominator, or backwards? So that's one way, right? The denominator grows faster, so that means we would be dividing by a larger number in the denominator. What happens when we divide by a larger number? Well, we get smaller. How small? Equals to 0. Another way to visualize this is to write this limit n approaches infinity, 2 over 5 to the n power. So what are we going to have in this case? Well, so in this case we have an exponential function f of x equals a over x, where if a is a number that lies between 0 but not equal to 0 and 1, we have an increasing function. Well, wait a minute, no, a decreasing function. And if we have a to be a number greater than 1, we have an increasing function. So in this case, what's our a? We have a 2 over 5. That number is between 0 and 1. So that has to be a decreasing function. Well, how about we verify this using our graphing calculator? So we're going to have, oh my god, mode, function. And that's open parentheses 2 over 5, and that raised to the x power. Well, in this case it's x is a function and graph. So what do we have? We have decay. What's going to happen for large numbers of n? Where is it going to go? Is it going to blow up to infinity, or is it going to converge somewhere? Converges to 0, all right? So the related function in this case is that of a decaying exponential. So in this case, this will be 0, and it means that converges. So in this case, this confirms what we were predicting by looking at the sizes of the infinities, one in the numerator and the one in the denominator. So 5 to the n is larger than 2 to the n, and having that 5 to the n in the denominator, of course, that makes us divide by a larger number, essentially getting a 0 eventually for larger numbers. So let's look at a similar situation for letter F. So this time we have 7 to the n over 3 to the n. So the number one thing we do here is limit 7 to the n over 3 to the n by analyzing each infinities individually. So which of these two infinities is the larger? Is the 7 to the n or the 3 to the n? The 7 to the n. So that means this time we're going to have a bigger infinity in the numerator dividing by a smaller number. Well, the infinity in the numerator wins, so that's going to become actually, well, let me write it down as n limit 7/3 to the n power, and in this case this a, it's a number greater than 1, so that should mean an increasing function. Let's verify that graphically. So let me change this to 7 over 3. See how this time we have an increasing function, an increasing exponential function? Well, so that means that for larger values of x, or n in this case, that's just going to blow up to infinity. And in this case, diverges. Right? The argument here, if you are given anything like this on the exam or on a quiz, just write down larger infinity and smaller infinity. Or write down as well, so that's one way. The other way is the related function f of x equals 7 over 3. The whole thing to the x power is that of an increasing function. So somehow we need to justify why is this positive infinity and why is that, or why is it a negative infinity. Yes, I mean, it looks like, yes, that's infinity, but we can either go with analyzing each infinity or taking the function as a whole and just saying that it increases or decreases like in the previous case. All right, so there's a couple of ways to justify this. All right, let's look at letter G. Letter G, that's what do we have? N factorial quantity squared divided by n minus 1 factorial times n plus 1 factorial. So what do we need to do in this case? We need to simplify factorials the same way we did it in the previous example, in the previous page. All right. Well, number one, we have this n factorial quantity squared. So, well, number one, let's write this as a limit problem. Limit n factorial times n factorial. So I'm going to write this n factorial squared as n factorial times itself. N minus 1 factorial times n plus 1 factorial as n approaches infinity. All right. So we need to simplify factorials, and let me group. I will group these factors. I'm going to group the n plus 1 with, the n factorial with n minus 1, and I'm going to group the other n factorial with the n plus 1 factorial. So let's focus on the pink factors right here. So between n and n minus 1, which of the two is the largest of the factorials? Is the n factorial or the n minus 1 factorial? The n. So that's the one I'm going to expand. So limit n times n minus 1 times n minus 2. Well, I don't think we need to go all the way to n minus 2, n minus 3, because that n minus 1, it's already matching the one in the denominator, the one that I have highlighted in pink. N minus 1 factorial, so n minus 1 factorial. Now let's expand the factorials in green. So between n and n plus 1 factorial, which of the two factorials is the largest of them? The denominator. So we need to expand n plus 1 times 1 less, which is n factorial. Well, it would be n. Then it would be n minus 1, n minus 2, etc. But because the minute we get to the n rather, this one matches the numerator, which is the n factorial. So we may go about canceling the n minus 1 factorial with n minus 1 factorial, and we can cancel n factorial with n factorial. This will leave us with the following. Well, let's write down whatever survives the cancellations, and in this case is a limit of n over n plus 1 as n approaches infinity. And what's this limit equal to? Zero. Well, what do we have? Doesn't that look like polynomial over polynomial? And what are the degree? What about the degrees of the polynomials? Don't they match? So we can go about the ratio of the leading coefficients, but these leading coefficients are invisible ones. 1 over 1, which is 1. Well, what do we do this cancellation or this simplification of factorials? Because check this out. Imagine, just like 5 factorial, 7 factorial. Imagine what would infinity factorial will be. Come on, really big over really big times really big over really big. Well, that's essentially the in this case the infinity over infinity indeterminate form. So in this case we need to do some algebraic manipulation to simplify these factorials, leave our expression without factorials and a simpler rational expression, and in this case, well, we get a 1. Let's do one more. Limit ln of n divided by n as n approaches infinity. And well, the first thing we do every time we have a limit expression, a limit problem, is the direct substitution. So number one, what would be limit of ln as n approaches infinity? Infinity, and n, well, that's also infinity. This means infinity over infinity, which is good. That means it's an indeterminate form. We can do some algebra over here. However, in this case, there's nothing we can simplify about factorials. There's nothing we can simplify like by factoring or rationalizing any denominator or multiplying numerator by some kind of conjugate. So we don't have any algebraic possibilities to compute this limit. So in this case, we would have to go about, any ideas on what to do? How do we go about this limit? Anyone? Not the exponential, because we are not solving an equation in this case. So we're trying to compute a limit, not to solve an equation. Any other ideas? L'Hopital's rule. All right, thank you. L'Hopital's. So that's limit n approaches infinity, and take the derivative of the numerator and take the derivative of the denominator. This is not the quotient rule. Be careful, not the quotient rule, but rather the derivative of ln, which is 1 over n, the derivative of n, which is 1. So in this case, well, we need to simplify this so we can compute the limit. That's 1 over n, and well, in this case, 1 over n goes to 0, and that's well, 0. This means this sequence converges and converges to 0. The previous one, I forgot to write that it also converges, and it also converges to this value of 1. All right, let's see what do we have next. So sequences have a few more properties, well, so we can expand some of these terms. We can determine whether they converge or whether they diverge. But if we further analyze sequences, looking at their behavior, these sequences increase or decrease, or they're called monotonic if they have only one kind of behavior. That is, whether they increase only or decrease only, because there are sequences that do both, increase and then decrease, increase and then decrease. That's not a monotonic sequence. That's just, well, it has a special name that we will discuss later. But in the meantime, well, what's the picture for an increasing function, for an increasing sequence? Well, let me do a couple of graphs. So let's relate this sequence to a function that also increases. So for example, for n equals 1, that's 0, and then it just goes increasing. All right. So we're going to choose some a sub n, whatever it is. This is some a sub n. The next term in the sequence would be a sub n plus 1, and then a sub n plus 2, a sub n plus 3, etc. That'll be just the next term. So in this case, the sequence is called increasing if a sub n is less than the next one, a sub n plus 1. And in this case, we can see that a sub n it's below a sub n plus 1. The height is smaller than a sub 1. And in the decreasing case, we can have the same essentially. I'm going to write different colors. So a sub n plus 1. Well, in this case, it's decreasing whenever we focus on one term, and the next one is actually smaller. So, well, a sub n is larger than a sub n plus 1. So that is, it's larger in value than its next term in the sequence. So this is what we call a monotonic sequence, by the way. a sequence that only increases and a sequence that only decreases, because we may have a sequence like this, you know, something like the sine function, if you will. If it becomes a sequence, for example, we just get discrete values like the first term, the second term, etc. Notice how at some interval goes up, increases, then decreases, increases again, decreases again, and well, so in this case, it's not a monotonic sequence, it's something else. All right? Now, so for the next example,